All right, let's get started. Okay, so did you start lab 2 already? No, not yet. Yeah, so I suggest you to start it as soon as possible. Yeah, because I think lab 2 is relatively straightforward. If you follow the instruction, it should be pretty straightforward. And then, so although the lab 2 will be due next weekend, but we're going to start lab 3 probably in the beginning of next week. Okay, so lab 3 is also a very straightforward lab, just to teach you how to use the software-defined radio that you purchased. All right, okay, so let's give a brief overview of our previous lecture. So the date is wrong, so it should be lecture 11, so I will change it afterwards. Okay, so in the last lecture, we focused on the power spectral density. So we didn't talk about modulation yet, which we're going to talk about today. So here, yeah, so we start from a power signal. So you can imagine GT as, for example, like a periodic signal, okay? And this is our definition for power, right? So basically, we compute the energy within the interval of t, and then we normalize it and let t go to infinity, right? So this is how we compute the power. And so now we want to, sort of manipulate it and to compute this in the frequency domain, right? In order to do that, so we define another function. It's called g capital T. So for this function, it is nothing but, so within a range of t, it equals to g of t. Otherwise, it's equal to 0, right? We just, it's a truncated version of the power signal, right? And then given that, we can do the following manipulation, right? Because of the Parseval's relationship, we can rewrite this part as this, right? Because so now the G capital T is an energy signal, right? So because it's truncated version, right? So for energy signal, we can compute the energy in the time domain. So that's also equals to the energy in the frequency domain, right? That's how we get this formula. And here, let's assume that so this function behaves well. We could exchange the limit and the integral, right? And then we could have the following equation, right? And here we can see, so it is the integral of the integrand over the frequency, right? And this is some form of the density, right? Since the integral of this guy equals to the power, then we call this integrand as the power spectral density. Okay, so this is how we came up with the power spectral density, and we denote it as G of F, right? And so this is basically the power spectral density, right? And you can see computing that it may not be easy because we need to compute this guy, right? So this guy is related to G of T, but it's not G of T, right? Normally in practice, so it's not that easy to compute this guy. So we need to figure out another way to compute it, right? Here are some properties of the power spectral density. So basically for a real signal, so power basically equals to 2 times this guy, right? And then, if we want to compute the power in a certain band, we just do the integral, right? And then we could compute it. All right, okay, so in order to compute the power spectrum density, it is similar to the way that we can compute the energy spectral density. So basically, what we do is that we define an autocorrelation function, right? And we can show that the Fourier transform of the autocorrelation function will be equal to the power spectral density, right? So this relationship is extremely important, and so we use that a lot in practice, right? For all the signal analysis, we're going to use this, right? So we compute the autocorrelation function, and then we estimate autocorrelation function in practice because everything is random. Right, and then we can estimate the power spectral density, right? So this is what we always watch, in practice. So very good, and so this is the definition of the autocorrelation function. So it's nothing but the inner product between G, T, and G star of T minus tau, which is a delayed version of GT, and then we integral that over this range and normalize it by T. Okay, and so again, you can see this definition sort of makes sense, right? Yeah, and this relationship is also called the Wiener-Hinchen theorem, And as I said, right, so we use that a lot significantly, especially for the random signal in practice. Okay, and here is an example as what we have studied so far. So in most of the cases in our class, so for the power signal is a periodic signal, right? So if it's periodic, let's see how we could compute the autocorrelation function, right? So those are some manipulations. We did that exactly in our class. You can see how we did that. So basically, the conclusion is that the autocorrelation function equals to this nice formula. You can see that sort of makes sense, right? Because so this is nothing but the Fourier series coefficients, norm square, and then multiply this complex exponential term. Okay, so that is kind of like the synthesis equation of the Fourier series, right? The only difference here is that now instead of Sm, we have a Sm norm square, right? So that's very intuitive, right? Because so this related to power, right? Okay, and there's another alternative representation. We didn't emphasize that in the class, so you can take a look. So that can make sense, right? And so after computing our autocorrelation function, so we need to do a Fourier transform of the autocorrelation function, right? And in this case, so because the Fourier transform operator is linear, then we can shift this Fourier transform operator from here to inside, right? So we just need to do a Fourier transform of this complex exponential function, and then we can get a delta signal, right? So this basically means that the power spectral density of a periodic signal equals to this formula, right? So we just need to compute the Fourier coefficients, so Fourier series coefficients, and then multiply a delta function corresponding to the frequency component, and then we're done, right? So yeah, every time when I ask you to compute it for a periodic function, you just need to compute S sub m, right? And then basically you're done, right? Any questions so far? Yeah. Okay, great. Yeah, and we didn't cover the random signal case. The computation of that is very complicated. You can, yeah, I'll upload my lecture notes of the previous lecture, and you can see how I can compute it, right? So it's very complicated. I think if I go over that in class, it'll take a class to cover it. It's just complicated, it's not hard. Okay, but the important thing here I want to emphasize a little bit is that, so when we compute the autocorrelation function for a random signal, it can be tricky. So we focus on this kind of particular signal. It's called ergodic signal, right? So it basically means that the time average equals to the ensemble average, or the time average equals to the expected value. Okay, so it's called ergodic, yeah. And in practice, we always focus on this kind of signal. Okay, in this case, we can show that the autocorrelation function equals to this guy, right? The difference between this and the previous case is that we have expectation over here, right? This expectation is from the ergodicity property, basically. Okay, and you don't need to understand how we get it, but just need to know this equation. I think that'll be enough. And from here, we can move this expectation inside, and we can see that, okay, so in this case, we just need to compute the expectation of this guy, and then do the integral, and then we're done. Okay, and computing this can be tricky in practice. Okay, and you can see how I do that in my lecture notes. Okay, so basically in practice, so this is a signal that we care about. We'll probably see this kind of signal again this class or next class, okay? And so this is how we transmit a digital signal in practice. So basically we have waveform, so that's a square waveform. From 0 to t is just 1, and everything else is 0. And we kind of modulate it, or we multiply either 1 or -1 to this kind of signal, okay? Just we transmit a square. If it's 1, it's just a square on the positive side. If it's -1, it's a square on the negative side, and so on, right? But if whether it is on the positive side or negative side is random, okay? So for this specific, if you have this special signal structure, the computation is manageable. Still complicated, but it's manageable, right? So, yeah. And we can see the lecture notes for details. And yeah, that's what we covered in our last lecture. Yeah, any questions? Any questions? Okay. So if no questions, so from this class, we're officially talking about communication. Okay, it doesn't have to be wireless, but communication. Okay, so the first topic we cover here is modulation and demodulation. Today is our lecture number 12, I guess. Modulation and demodulation. You can see it should be somehow like reverse operation, right? But in practice, is no. Yeah, you can see how we do that. It's kind of interesting. And so there's a very nice structure happening here, okay? And so I think this is in our chapter 4. So if you want to take a look at the book, just look at the book. Okay, and we're going to focus on modulation today probably, and let's see how far we can go, and then we can cover the demodulation part. Okay, and now let's give you a few definitions of modulation. We've definitely seen this many times already in our class. Okay, so we're going to officially introduce it and see, like this g of t multiplied cosine 2 pi ft, so that's a modulation. But today we're going to officially introduce it and see what kind of modulation that is. Right? There are so many kinds of modulation. Okay, let's see the most general definition of modulation. Okay, so this is modulation. The most general definition. Yeah, we sort of mentioned this a few times. Yeah, so based on your understanding, so what is modulation in words?
Like transforming a signal to carry information.
Transform a signal to carry information.
Like transforming the amplitude of a signal to carry information. So wouldn't it be more like changing the factor of the signal to transmit information?
Yeah, I think, all what you said are correct, right? But so what I'm going to write down is even more general than what you said, right? So these are the most general. Yeah, definitely. What you said is amazing. So they're all correct. Okay, so the most general definition of modulation is nothing but it's just a mapping of information to a signal that can be transmitted. That's it, right? So it's kind of very obvious, right? The mapping of information to a signal that can be, that is, yeah, I'll just write down whatever I have here. That is appropriate for transmission over channel. Right, so basically, it means a lot of operation and steps, can be understood as modulation, right? But here we're going to focus on kind of a narrow definition for modulation. Okay, like mapping, if it's digital, we're mapping bit to some kind of signal, that's modulation. And then we move the signal from one frequency to another frequency, that's also part of the modulation, right? But in this class so far, so we're going to focus on a very specific definition of modulation. It's called carrier modulation, right? Basically, yeah, this is, where we talk about we shift signal from one frequency band to another frequency band, right? So this is what we care about so far, right? So we're gonna do other stuff later in this class. Okay, so first let's see what is the definition of carrier, right? So what do we mean by carrier? Yeah, I sort of just explained, right? So carrier is nothing but a sinusoid or a complex exponential to move the signal from one band to another band, right? So that's the definition of carrier, right? Okay, let's write it down. So sinusoid, a sinusoidal signal used to move. So here, when we say we move a signal from one band to another band, and in practice, since everything is random, so we talk about the power spectral density instead of the bandwidth of the signal, okay? Because this is well defined, right? If a signal is random, then so it's very hard to define what's the bandwidth of a signal, right? If we do the Fourier transform of a random signal, then we still have something random, right? But PSA is not random; it's deterministic. Okay. Oh, by the way, so why the signal that we transmit in practice are all random? There's no deterministic signal. Right, so in practice, all the signal for communication, right, are random. Why is that? Yeah, noise, very good, right? So the air, whatever, all the channels in practice are noisy, right? So there's no clean channel. We have lots of noise in the channel. Yeah. Any other reasons? Yeah, noise is one factor. Yeah.
Like the different molecules in the air, they kind of like distort different
Very good.
frequencies differently.
Definitely, very good. And basically, what he said is that we have different kind of the channel gains. Right? The channel will have different impacts in different frequency band on the channel. It's not noise, right? It's something like the signal multiply a factor. Right? This factor is the channel gain. Or in practice, the channel we have is so-called multi-pass channel, right? As a receiver, we can receive different versions of the signal, but it's delayed. Right? The channel in this case is what? It's kind of a system, right? We do a convolution between the transmitted signal and the channel, okay? But this channel is normally random, right? Any other reasons? Yeah, the other reason is kind of not obvious. So basically, we have no idea what is transmitted, right? For example, in the receiver, I have no idea what is transmitted from the source, right? If I decode it, I know it. If I don't decode it, I don't know it, right? So normally, I model the source also as a random process, right? The information to be transmitted are random, right? Does it make sense? So if the information to be transmitted are not random, are deterministic, then we should know it, right? Because it's deterministic, right? We don't need to transmit anything, right? Because of the source is also random, that's why we need to transmit it, right? So the source is also random. Yeah, like the A we just showed in the slides, right? If A is equal to +1 or -1, so this +1 and -1, they're randomly distributed. Okay, you can see there are so many random components in a transmitted signal. So in practice, the transmitted signal are random. Okay, and for random signal, well, in the frequency domain, we always talk about PSD. Let's assume the signal is extremely long, right? So, okay, yeah, a sinusoid signal used to move the PSD of a message. Of a message signal to a different frequency band. Okay, that's a carrier. Okay, so now let's see what is the carrier frequency. Okay, so basically it's very obvious, right? The carrier frequency is nothing but the frequency of this sinusoidal signal, right? Yeah, that is the frequency of a carrier sinusoid. Okay. And this frequency of a carrier sinusoid, so that is normally denoted as Fc. So this C means carrier or F naught. Okay, so we normally denote that in using these two notations. Okay, that's all the simple definition we want to introduce. So next, let's see the modulation that we have been seeing so many times, right? So basically, what we're going to see is this guy, g of t multiply cosine 2 pi fct, right? So normally, the transmitted signal is denoted by s of t, right? So that's the simplest kind of signal, the modulated signal that we have been seeing, right? That can move the signal in the frequency domain, right? Using the property of the Fourier transform or the property of the cosine signal, okay? And for this simplest version of the modulation, so we have g of t is the message signal, right? G of t carry information here, yeah. Yeah, let's use a different notation. Because it's a message, so in practice, normally we denote this signal as M instead of G. Right, use M here, meaning message. Okay, and the cosine 2 pi fct, so that is our carrier. Okay, and you can see that. So for what is M of t here, right? So M of t is something in front of cosine, right? It's kind of the envelope of the signal, okay? So basically, if we have this kind of modulation, it basically means that the envelope carries information, or we call that amplitude, okay? And this is a special type of amplitude modulation. That makes sense, because the amplitude of the signal carries information. And this S of t, of course, that is called modulated signal. Okay. Yeah, that's all the definitions here. And we have seen this many times already, but yeah, let's recap it, right? So if we have a signal in time domain, the modulated signal in time domain like this, and then in the frequency domain S of f, so what does that equal to? Okay, so assume the Fourier transform of mt is capital MF. So what does that equal to? Yes?
Multiplication by complex, or I would say frequency shift.
Yes. And can you tell me the formula exactly?
Capital M of f minus f naught.
Or FC. Let's use FC here. Very good. Yeah, and
Plus.
yeah,
Minus plus f naught.
very good.
1/2 also.
Very good. Yeah, we have a 1/2 here because this 1/2 coming from the Fourier transform of the cosine, right? So this is basically the modulated signal. And yeah, if we have the original signal in the frequency domain looks like this. So let's say here is MF. Let's say here's 1. And then for the modulated signal, so we just shift this guy to both sides, right? And here's minus FC, and the magnitude here is 1/2, right? This is S of F. Okay, yeah, just recap a little bit, right? We'll move the signal from the lower frequency part to a higher frequency part. Okay, so that's what is happening here. Any questions? Okay, if no, so now let's generalize it, right? So this is where we start from. Okay, so now let's generalize this form to make it, more general. Okay, let's see what we're going to do. So first of all, so now as we said, right? So for this signal, this amplitude carries information, right? So can any other part of the signal carry information? Right? Can the frequency part carry information? Or we don't show a phase part here. Usually, there's a phase here as well, right? Can the phase carry information? Okay. So basically, the answer is yes to all of them. So yeah, let's see what is the general carrier modulation. Okay, so a general carrier modulation is given by the following form. We still have our modulated signal, but that equals to, now we change the notation to A of t. Okay, and then we times cosine. So the idea is very similar, right? So we have our carrier frequency fc, but here let's say we have another frequency component denoted by delta f, right? And then t. And then we have another component, which is a phase. Okay, so all of them can be a function of t. This delta f can be a function of t, and this phase can be a function of t as well, right? So basically, let's give some name of it. So this is the amplitude. Okay, and this is frequency. And this is phase. Right? For this, for this phase, you can basically understand this as the phase component for the complex exponential. Right? If we add j times sine of this guy, and this, we can take that out from the complex exponential. Right? That's a phase term. Okay, great. Yeah. Any questions so far? Okay, and from here, so we can see that because this is a function of t, right? And this can be a function of t, and this can also be a function of t, right? So basically, it is possible that the changing of this part is the same as the changing of this part if this part carry information, right? So basically, it means that if we don't have this, it's a constant, then so this frequency changing can carry the same information, right? And similarly, so if we don't have this delta, this delta f is 0, and this at is 1, and if the changing is carried here on the phase part, so this can also carry information, right? So these three places, all of them can carry information, right? So basically, from here we can see we have three types of modulation, okay, that we use in practice. Okay, let's summarize it. So we have three main type of modulation. So here, because we are doing analog transmission, so in general it's called analog modulation. Okay, and we have three types of analog modulation, and the first is when AT carries information, so that's called amplitude modulation. Okay, so now let's denote our message signal as m of t, right? So let's say that's our message. Then A of t, we don't need to require A of t exactly the same as m of t, right? It is okay to assume that, yeah, right? But yeah, because we're talking about more general case, so for the amplitude modulation, so our requirement is that AT varies with m of t, okay? So A of t is a function of m of t, right? As long as we can, decode how AT varies with m of t, then we can decode m of t, okay? The second type of modulation is called frequency modulation. Frequency modulation. Okay, so here similarly, so here basically means that delta F varies with m of t. Okay, and the last one is called phase modulation. And it means that phi of t varies with mt. Okay? Yes?
So for the frequency modulation,
Uh-huh.
can you multiply it by f of c, or is it always just adding?
I mean, FC multiply that?
Yeah.
Yeah. Probably not. Probably no. Yeah, I've never seen something like that before. I think the important thing about this design is that we need to make sure that we can demodulate. Yeah, you can try. So the frequency modulation is pretty complicated, and later you're going to see the demodulation is very complicated. Yes, even in this form.
Is there ever any scenario where you use multiple at the same time?
Multiple what?
Like modulations?
Oh, at the same time?
Yeah.
Good question. I think so. Yeah, based on my understanding, at least I think we can do that. I think we can use AM and FM at the same time. Yeah, you can see why we can do that, but I think so. Yeah, very good question.
Does that just like make it? Is there any reason to do that though? Does that like add more security or something?
Yeah, that part I don't know, but technically I think that's doable. I think it's not. So in practice, I don't think the performance of doing both is the same of doing each individual ones. I think there's some performance loss probably. Yeah, but mathematically, I think you should be able to do that. Yeah, but I have to check it offline. I'm not sure. But in practice, I don't think we do that very often, at least, right? Because when you listen to the radio, you have FM, you have AM. FM is frequency modulation. AM is amplitude modulation, right? You don't have those combined, I think, right? Well, by the way, so when we talk about AM, it doesn't mean this. It doesn't mean amplitude modulation. It is, the word is amplitude modulation, but it doesn't mean, for example, this, right? So AM is a very specific type of amplitude modulation that we're going to talk about, right? It's I think it's the, how to say, the simplest AM modulation. The receiver, the demodulation is incredibly easy. So that's why, the performance is not good. If you listen AM signal, I think it's pretty noisy compared to FM. So FM is much better in general. Okay, yeah, very good question. Yeah, they're all excellent questions. Okay, yeah, any other questions? Yeah, if no, so we're going, basically our agenda is to talk about them one by one, okay, in the later a few classes, many classes, I think. So because some of them is very complicated. So AM is the easiest one, so we're going to start from here, okay. Okay, so for amplitude modulation, so we're going to go back to our original consideration. So consider the simplest case, right? ST equals to MT times cosine 2 pi FCT, right? So that's the same as what we considered before. Okay, so here, given this form, so we have two concepts to define. There are so many definitions in this class. So one is called the modulator. Yeah, what is a modulator? Right, so in practice, you always heard of this word. So a modulator, normally, so it means, so that is a circuit for generating the modulated signal. Okay, so in practice, how we implement this guy is something like this. So this is our input signal, and then we multiply this by cosine 2 pi fct, right? And then we have our modulated signal, right? Normally, although narrowly, so it means a circuit, to generate the modulated signal. But we always say, so the whole procedure is a modulator, okay? And here, in particular, in this case, so we have a very special operation here. So that is the multiplication. So this multiplication called mixer. Okay. So in particular, so the meaning of mixer is nothing but a device that can multiply two signals, right? So this means a device can multiply two signals, right? And especially one of them is a carrier, like what we're talking about here, right? So this is basically a carrier. In this case, the mixer does the multiplication between MT and the carrier cosine 2 pi fct, right? That's called mixer. All right, okay. And for example, so let's see a very simple example. Let's see this kind of signal that we introduced before. So it's kind of digital information. So by the way, for digital communication, so yeah, that is, usually when we refer digital or analog communication, so basically we mean, how to represent the information. Right? For example, if we want to transmit the audio or a speech, right? The signal looks like this, right? So if you transmit that exactly, so that's analog communication, okay? But for digital communication, we need to convert this kind of signal to, for example, 1 - 1 or 1 0, and then transmit those 1 and 0 or 1 and -1, okay? But all the information, all the signal we transmit over the air, they're analog. Okay, so all the transmitted signal, they're analog, right? So there's no way to transmit just discrete signal over the air, right? They're all continuous and analog. All right, very good. And given that, so I say digital information, meaning the information is like 1 - 1, right? Doesn't mean the communication is, the transmission is digital. Everything has to be analog, right? Let's assume the source information, AI, is in plus and minus 1 or -1. Okay, so we can consider that as information bit or message bit, and that is random in practice. Okay, so now let's assume our M of t, transmitted signal, is in this form. Sum over I, AI, we use pt, t minus tau. Okay, and here, so the definition of pt is the same as before that we see in the slides, right? It is 1 from 0 to t and 0 otherwise. Okay, so basically it means that, let's say if we transmit a signal, I say if we transmit 1, 1, -1, right? If that is, for example, let's say here is a 0, here is a 1, here is a 2, here is a 3, right? The actual transmitted signal looks like this. So at 0, we transmit a 1, so that looks like this. T, here is 1. And for the second one, it is still 1, so we transmit something like that, right? And for the third one, it's -1, so it means that we transmit something like that. And for the fourth one, it's 1 again, so we go up again, and so on, right? So here's 2 times t, here 3 times t, 4 times t, and so on, right? Here is A0 equals to 1, A1 equals to 1. Here is A2 equals to -1. Here is A3 equals to 1. Okay, so this is our MT. That clear? Right. So this is our time domain signal. And now let's see what the signal look like after this operation, or what the signal what S of t look like, right? Exactly. So in particular, yeah, let's consider a very simple case. Okay, so we just let Fc equals to 1 over t. So what does that mean?
The period of the carrier frequency of the carrier signal is t.
Yeah. So exactly. So basically, it means that our carrier look like this, right? The fundamental period of the carrier is t, right? So this is t. So basically, it means that the carrier, yeah, let's align them. It's a cosine, right? So this is one period, right? And this is another period. And this is another one, and so on, right? So now if we use this, multiply that, let's see what we got. And for the first information, the first one, so basically we got this multiply 1, so equal to this, right? Here's 1, here's 0. So this is A1 equals to A0 equals to 1. And for the second one, again, same thing. So this multiply that, right? Second one, same thing, which is nice, right? So here's t. But for the third one, so we have a -1 here, right? We use -1, use this, multiply that, right? So then we need to flip it, right? Because it's minus. So it looks like this. Right? And the last one is 1 again, so it looks like this. Right? This is A1 equals to 1. This is A2 equals to -1. A3 equals to 1. Does that make sense? Right? And you can see here, so we have something like this happening, so which may not be very nice, right? So this is a jump, right? The signal becomes not continuous. Right? But this is how the signal look like if we do this. So any questions? Okay. So for this special type of signal, right, because we have the only thing we transmit is +1 and -1, right? And so the modulated signal looks like this. So we have a special name for it. So let me see. Let me write it here. So actually, when you see something like that, right, this AI is +1 or -1. So we're talking about digital communication, okay? So for this kind of communication, it's called binary amplitude modulation, shift keying, or BASK. Okay, for example, the Morse code use this kind of Morse code. Use this kind of modulation, right? And also, the reason it's called amplitude shift basically, means the amplitude is changing, right, from 1 to -1 and so on. Okay, and later on, you can see if we have this specific form, okay, because if I have a -1 here, so we can actually do some manipulation about the cosine to move the -1 inside, right? So basically the operation we do is like plus and minus pi, right? So that's a phase shift, right? So the same thing. So we have another name for it. It's also called binary phase shift keying. or BPSK, right? Probably that is more generally used in practice. So we'll have same name we'll have two different names, but for the same modulation. Okay. Okay, very good. So, any questions? Yeah.
So, in order to make EASK, BPSK, it has to be 1 and -1, right?
Yeah.
Like if it was 1 and 0, it
Yeah.
would be BPSK.
No.
It would just be
No.
BPSK.
Yeah, we have a different name. It's called OOK.
Okay.
Yeah, I forgot what that means. but it's called OOK. So that's used in optical communication. It's like, if we transmit signal, it's 1. If we don't transmit anything, it's 0.
It's on-off key.
Yeah. On-off key. OOK. Yeah. Very good. Excellent. Okay, so now let's introduce more definitions. Okay, great. Okay, again, so now let's look at the signal from the frequency domain again. So we have S of f equals to half mf minus fc plus half mf plus fc, right? And so the signal looks like this in the frequency domain, as we have seen before. Okay, and this is fc, this is minus fc. Okay. And some of you asked me this question when we talked about this before. Okay, in some cases, the signal can be symmetric along this line, right? Sometimes it's not symmetric. Okay, but so actually, there's something we can do here. So we're not going to focus on that today, but there's some special name for different parts of this signal. Okay, so for example, for this part. Right, correspondingly, so that is, so if we look at the original signal m of t, m of f, so this part corresponding to kind of this part, right? So that is called what? The lower sideband. Right, because it occupied the lower frequency component. And for the other one, let's see whether it works or not. For this part, so that's called the upper sideband. Okay, so those are some names. And the other important observation here is that, so this is our modulated signal, S of f, right? And from here, so can we see any carrier transmitted? By carrier, I mean this cosine 2 pi ct, right? So there's no carrier transmitted. If there is, we need to have some delta function here, right? So no carrier present. Yeah, if it's not clear to you, then you'll understand what do we mean by this in the next lecture, right? We're going to add the carrier here, actually, in the next lecture. So there's no carrier present. Okay, so for this kind of signal, because we have both lower sideband and upper sideband, right? Let's say if they are symmetric, right? For example, if this guy is real, so we have totally symmetric, so we don't need to transmit both of them. We only need to transmit half of them, right? So, but if we transmit both of them, so we have a special name for this modulation. It's called double sideband modulation, or we call that DSB. Right? Does that make sense? Because we have both bands. And since we don't have this carrier present, right? There's no carrier transmitted together with it, okay? Then we're going to represent this information for the modulation type as well. So we called this double sideband surprised carrier, or DSB SC, right? This SC basically means that we don't transmit the carrier along with the modulated signal. Okay, DSBSC. Okay, so we're out of time. So next lecture, we're going to talk about the demodulation. Okay, so let me know if you have any questions. Okay, so see you.